right? Okay, so now let's come to the main business of this lecture. So we have now seen scenarios of light beams interfering, light waves interfering, right? Now we want to go a step forward and consider a fairly sophisticated scenario of multiple beam interference, which is going to be of immense interest to this course, okay? Because all lasers are made up of optical resonators, and this course is built upon lasers and particular types of lasers. So attosecond light sources, if you wish, are all based on primary optical or infrared lasers. So let's take this classic case of the Fabry-Perot interferometer. So what do we mean by the Fabry-Perot interferometer? Okay, what do we mean by the Fabry-Perot interferometer? This is what it is. So this celebrated iconic interferometer is nothing but a piece of high quality glass. The surfaces and the interior of this planar piece of glass are of high quality. That's they don't have any blemishes or scratches, and the surface is fairly planar. And these two surfaces, among other things, very importantly, are very parallel to each other. Okay, so this is really high quality optical manufacturing at work. Now, this glass piece, which is here, which forms the interferometer, I've shown it with finite boundaries, but let's not, in this idealized situation, even limit the length of this piece. Assume this to be really very, very large. And the material inside, that is the material constituting this high quality glass, has a refractive index N. So glass is made up of silicon dioxide, which is a wide band gap or a wide gap material. So for visible and infrared wavelengths up to about 1100 nanometers, the glass is transparent, okay? And it also, if it's high quality, it has no loss. It is lossless as well. Then we have three regions here. First, a region of air. On one side of the glass, you have glass, and second, another region of air. We will now set the refractive index of air for this discussion to be just one, unity, okay, on either side. Now, in reality, the refractive index of air is just a little bit bigger than one. Ideally, the refractive index of just vacuum is unity. Even air has a small difference in its refractive index from vacuum. The refractive index depends upon pressure and temperature and local density of air too. We are sort of ignoring all these inhomogeneities which could be present in real life. Even the room in which we are sitting now, there are inhomogeneities in the air around. But if we can choose to ignore that and yet be successful in implementing a Fabry-Perot interferometer of this type, so we will take it for that. But the most important aspect of this discussion is to realize that now on either side of this interferometer, which is essentially a piece of glass, we have two interfaces. One is a glass air interface, so we can go from glass in to air out, or we have an air glass interface going from air out to glass in. Okay, so now let's have a wave incident from the left to right. Okay, so this wave, which was incident from left to right, begins somewhere in the air region on the left side, that is our left side, and walks towards the right, and it encounters an air glass interface. So at this interface, of course, the wave can transmit through the glass, because glass, as we say, is transparent. But now, not all the wave amplitude of the incident wave E naught comes through. What comes through is a fraction of the incident wave, and the field amplitude of the transmitted wave is E naught t. Okay, so the wave amplitude, of course, has reduced owing to the following. When the wave walks through from air to glass, there is an air-glass interface. The ratio of the electric field amplitudes on either side needn't be equal. Okay, so on the inside of the glass, the amplitude of the incident wave written in terms of the original amplitude E has a value E multiplied by a coefficient, in this case T prime. T prime is the transmission coefficient of the air to glass interface. Okay, so the amplitude is diminished by a factor T prime, so therefore T prime is less than 1. It's between a number between 0 and 1. Okay, likewise, as the wave propagates and encounters the next interface, right, it comes out again back to the air side, and in this case it undergoes or walks through another interface. So just like we treated the air glass interface with the transmission coefficient that is T prime, the glass air interface also has a transmission coefficient, which is, okay, I should pick the right color, which is T. So T and T prime are the two transmission coefficients, and the wave that comes out on the right hand side, written in terms of the original incident wave amplitude E naught, is T prime times T multiplying E naught. Okay, first interface, which is air glass, second interface, glass air, and multiply E naught. Okay, so these two coefficients for transmission come to play. Now, not only does this happen, okay, we also should consider the scenario where at the glass air interface on the right, the wave can suffer a reflection. Okay, the wave got reflected from the glass air interface. Okay, this happens simultaneously and it is a natural phenomenon. Now, this reflected wave here, okay, has an amplitude E0R. Okay, now what fraction of reflection happens at this glass air interface? At the glass air interface, the coefficient of reflection which captures the fraction by which fraction of the wave which reflects at the glass air interface is the number R. Okay, so given the refractive indices of this medium, we can compute these quantities. Likewise, you must have guessed by now that even for the air glass interface, a reflection can occur, and the reflection coefficient for that quantity is R prime. So we have a reflection and a transmission coefficient for glass to air. We have a reflection and transmission coefficient for air to glass, which is R prime and T prime. Okay, so now we have all the tools to solve or address this very interesting physics problem. What do we want to know? We are going to want to handle the following scenario. Now, just as there was a reflection here to the right at the glass air interface, see where my cursor is hovering, at the next glass air interface, there is going to be a similar reflection. Okay, so the wave reflects from there and comes to the right. So now this is wavelet 2, which came out to the right and is transmitting along the same direction as the first piece of transmitted wave. So this is piece 1, this is piece 2. And now the question is, what is the amplitude of this second piece of transmitted wave, which I must write in terms of the only quantities I know before I begin addressing this problem. What do we know? We know the value for the amplitude of the incident wave, E naught. Okay, we know the reflection and transmission coefficients of this material glass kept in the medium, the surrounding medium, which is air. So we know E naught, we know R, we know T, we know R prime, we know T prime. So whatever we write down here and hereafter should be written down entirely in terms of the knowns, so that the unknown, that is E naught T, okay, can be computed based on these quantities. Likewise, you may want to compute E naught R as well, which we are not going to do here. You can do that as an exercise to test your own understanding, right? So now we computed what the first transmitted piece is in terms of E naught R prime, T prime, R and T. It simply turns out to be T prime multiplying E naught. What about the second case? So let's examine that and write down the answer for what should be the amplitude of what I will now call beam 2, which is here. This is beam or wave, piece of a wave or a wavelet, not a wavelet, that term means something else. Wave piece 2 over here. So this wave is going to have the following amplitude, okay? I derived this wave from E naught, so let me write down E naught. How did I get the beam out to, how did I get the second beam out? It started as E naught, it underwent one transmission here. So the transmission coefficient for this was T prime. Then it traversed to the other end or the edge of this glass piece. It got reflected here. So it got, there is a reflection coefficient R that is involved in that reflection. So let us write these two down. So we have T prime. We have a reflection here at the first interface. I'm bubbling that interface now. So there is an R. The wave traversed. We are going to consider this traversal of the wave from one end of the glass slide to the other. It reached the second interface and suffered another reflection. So there is a second R involved over here. Then there is propagation through this piece of glass, and it exits the glass piece from glass to air. So there is a factor T. The transmission coefficient is also included here. But what about the transmission through this glass itself? It transmitted freely through this glass. It went from left to right, right to left, and then here, right? So now we are going to consider this in the following manner. We began this exercise all the way from, sorry. We began this exercise from here to here, okay? So it went from left to right and then right to left. So this propagation involves a phase delay. Recall that we had the concept of phase delay, which we learned in our earlier lecture. The phase delay that essentially comes about due to this propagation leading to the second piece of the beam, which is 2, for beam 2, has the value e to the minus I delta. This is the coefficient. This is the factor that captures this phase delay. So what is delta here? Delta, which I've written down here, is essentially the phase delay owing to one round trip. The round trip goes like that. Okay. What is L? L is the total length of the round trip path. It goes from right to left to right here, from edge to edge. This is approximately twice the thickness of this piece of glass. It's not exactly the thickness of the piece of glass. It's close to that, but the deviation from that is also important, as we will see later. Okay, so we wrote this down for this piece of glass. So the transmitted wave 2, that is after doing one round trip in the glass, is essentially T prime R square e to the I delta. Now, after this, the wave is again going to, we can create another beam by doing one more reflection, another reflection, and creating a second round trip. Let's look at that. The wave goes, it gets a second reflection, and then this forms the third piece of the total transmitted wave. So we can now write down, okay, just by inspection, the transmitted amplitude of the third piece of this wave. What is the transmitted amplitude going to be? it is everything being the same. There is TT prime, there are two transmissions involved, but compared the difference between the second piece which did one round trip and the third piece which did two round trips is just the number of round trips. And each round trip modifies the wave amplitude by a coefficient r square e to the I delta. Two reflections, r times r, and one round trip propagation e to the minus I delta, right? So therefore, for the third piece, it is TT prime multiplying r square e to the minus I delta twice. In fact, by inspection, we can more or less write down what the fourth piece is going to be. It is r square e to the minus I delta cubed multiplying E naught and so on and so forth. So the total transmitted beam will contain now terms of this type. The total transmitted wave is a sum of all these waves which are propagating in the forward Z direction if my coordinate system has this as the Z axis. It's more a matter of convenience. Remember that L is the round trip path length and delta is the round trip phase delay. Okay. So now, in terms of the quantity of interest which we want to compute here, this is the total transmitted field, which is E naught T. E naught T is a sum of the wave that the piece of the wave that transmitted through without any round trips, plus the wave that made one round trip, plus the wave that made two round trips, plus the wave that made three round trips, plus 4, plus 5. It's an infinite series. Of course, you can see that these terms of the series are diminishing because each reflection coefficient is less than 1. So the series is indeed going to converge. And the sum of this series is, we know, nothing but 1 divided 1 minus this common factor, r square e to the minus I delta. So the total transmitted amplitude is TT prime multiplying E naught times 1 divided by 1 minus the common factor, which is r square e to the I delta. Now, this is the transmitted amplitude. The transmittance is the corresponding quantity for irradiance. That is the transmitted irradiance, which we call transmittance. Welcome to optics terminology. So this is essentially transmitted irradiance, but you may also come across this as transmitted intensity or transmitted power, all of which are similar quantities, is the following. So T, the transmittance, is the absolute value squared of E naught T divided by E naught, the transmitted wave electric field amplitude divided by the transmitted or the incident electric field amplitude, square of this ratio after considering taking its absolute value. So looking at the expressions here, so E naught T essentially is TT prime divided by 1 minus r square EI delta multiplying E naught. So this quantity is now TT prime divided by 1 minus r square e to the I delta. It's the square of its absolute value. Okay, so now we want to simplify this even further, which we indeed can, by considering the next quantity. That quantity is R, which is now reflected irradiance or the reflectance of the same scenario or quantity, right? So what is capital R? Capital R is essentially the square of the individual reflection coefficient or the amplitude reflection coefficient little r. Okay, so little r corresponds to amplitude, field amplitude. Capital R corresponds to irradiance or intensity. Now, we use these relations, that is r square is r and t prime is 1 minus r. These relations arise from the fact that the medium is lossless or entirely transparent. Okay, the glass, we assume a perfect piece of glass with refractive index close to 1.5. So then a lot of things get simplified. We have here the same equation for the transmittance T, now written in terms of the reflectance. Reflected irradiance is, of course, called reflectance. Reflectance R as 1 minus r squared, that is T prime is 1 minus r, and the absolute value square of the numerator brings up 1 minus r squared, divided by the denominator 1 minus r e to the minus I delta, multiplying 1 minus r plus e to the power plus I a delta. Okay, so a little bit of simplification of the denominator. So we can now write this expression down in terms of cosine of delta. So this turns out to be 1 plus r square minus twice r cosine of delta, but a trigonometric identity tells us that the cosine of delta is 1 minus twice the sine square of delta by 2. So exploit that and then further figure out that this term here in the denominator, the first three terms of the denominator sum up to 1 minus r the whole squared, and then we have 4r sine squared delta by 2. Now this leads us to a very elegant expression. If I divide the numerator and denominator by 1 over r squared and set 4r by 1 minus r squared to a quantity f. So if I set f is equal to 4r by 1 minus r squared, then I can write down the transmittance in terms of just two quantities or numbers. One is f, 4r by 1 minus r squared. F depends only on the reflectance of the material, that is glass, in a given medium, which is air here. And delta. Delta is k times L, where L is the round trip path length and k is the magnitude of the propagation vector, which is 2 pi divided by lambda. Okay, so let's plot t as a function of delta. Okay, since f for a given echelon or Fabry-Perot, f is a constant because r is fixed. Okay, so now we are plotting the transmittance for three different values of f. The first value is f is equal to 200. The second is for the case of f equals 1. Third is a rather poor f. It is f is 0.2. F is equal to 200 corresponds to an R of 87%. This is basically reflectance also is a number between 0 and 1. We have multiplied that by 100 so that it can be written as a percentage. And this R is, again, for f is equal to 1, R is 18%. Here for f is equal to 0.2, it's a really poor reflection, which is R is equal to 5%. Okay. Now, these different f's essentially correspond to transmittance curves, all of which peak at a transmittance of unity. That is, maximum transmittance is unity. That's a consequence of the fact that this glass is lossless, essentially. Okay, there is no loss involved in the physical description of what we have done so far. And we essentially, the only feature that differentiates these three curves, the red, green, and the orange, are essentially the sharpness or the widths of these lines. That's that, as well as the fact that for relatively poor or small values of f, the minimum is not 0. Okay, the minimum transmittance is further and further away from 0. Okay, it is getting closer to unity. So the contrast diminishes. So that's a feature of how the transmittance depends upon the quantity f, which is 4r divided by 1 minus r squared. Furthermore, the location of these maxima are the other important feature which we need to consider. The maxima occur whenever delta is an integer multiple of 2 pi. The trivial 0, we have then 2 pi, the next maximum at 4 pi, 6 pi, and so on the positive side. This could also sort of take negative values relative to where we set the 0. It is minus 2 pi, minus 4 pi, and so on and so forth. Or delta is divided by 2 is equal to m pi, where m is an integer coefficient, essentially tells us where the maxima are placed on the scale of delta, which is a phase. It is k, the magnitude of the propagation vector, that is 2 pi by lambda, times L, the round trip path length, which we are considering here, right? So in other words, if I were to now ask, if I fix L, okay, at what lambdas or what wavelengths will I have maxima, I can essentially figure that for a given L, I would essentially have maxima occurring for wavelengths which satisfy L divided by an integer m. So it for lambda is equal to L, lambda is equal to L by 2, L by 3, and so on, where L is the round trip length. It's not the thickness of the glass slide. Okay. So transmittance now varies as a function of delta, and delta essentially can be varied by varying L. Okay. It is 2 pi L by lambda. So it can be varied by varying L. It can also be varied by varying lambda, right? So I can take an echelon and I can sweep the wavelength of the incident wave if my source is tunable and measure the transmittance. Then the transmittance would find itself a maximum, go through something close to 0. If the f is large, find a maximum and go through 0 and maximum and so on as I sweep the wavelength for a given echelon and a geometry. I could also have figured out scenarios or ways to change the L. One way to change the L is to change the thickness. Okay, so maybe you can heat it or you can apply some electricity if it's a piezo and use the piezoelectric effect also to sort of widen or stretch your medium if it has a good piezoelectric coefficient. But more sort of important or easily, you can change the angle of the glass piece forming the echelon with respect to the incident wave. That would also effectively vary the L, that the round trip length, and that could also lead, that could also be a way to tune delta so that we can reproduce this transmittance curve in experiment. Okay, so the features again, as f increases, the reflectance, that's the reflectance of the surfaces involved, reach unity. Very good reflectances, reflecting surfaces or interfaces. The transmission becomes high in contrast and narrow in its width.